Hello, my name is Katherine Smith, and welcome to a new episode of Calculus Daily. Broadcasting live from Markham, Ontario, today we will be showing the nation how to solve a mind-puzzling problem sent in to us by one of our fans. The question that was sent in states, a fruit fly infestation is doubling every day. There are 10 flies when the infestation is first discovered. Next, the question is split into 5 parts. First it says, write an equation that relates to the number of flies to the time. The next part says, determine the number of flies present after 1 week. Part C asks, how fast the fly population is increasing after 1 week. The next part asks, how long will it take for the fly population to reach 500? And finally, the last part asks, how fast the fly population is increasing at this time. It is evident that this must be question number 6 from page 274 of the McGraw-Hill-Ryerson Calculus and Vectors textbook. Oh, how I remember grade 12. What a riveting year. This question is obviously from Unit 5, Derivatives of Exponential and Logarithmic Functions. It is clear that this question originates from this unit as it states that the fruit fly infestation is doubling every day. The fact that the question states the population will be doubling means the population will be increasing exponentially, in turn proving the function is an exponential function, which is a part of Unit 5. Another key part of the question we want to recognize is that it says doubling every day. This means our time unit will have to be in days. Today on Calculus Daily, we will analyze each part individually and then explain step by step how to solve them. To conclude, we will discuss an overview of what you need to do to solve a question such as this one, while also touching briefly on what careers you could find a problem such as this one in. So let's begin! To refresh, the question states a fruit fly infestation is doubling every day. There are 10 flies when the infestation is first discovered. Part A of this question says, write an equation that relates the number of flies to the time. As this is an exponential function, we will follow the form P of t is equal to a times b to the exponent of t. P of t represents the population at a given time. A represents the initial population. In this case, a will have a value of 10, since this is the initial population when the infestation was discovered. B represents the base of the exponential function, but it also represents the rate of change. In this case, the rate of increase is doubling, so the b value will be 2. Finally, t represents any given time in days after the infestation was discovered. With all of these factors taken into account, we can create the equation. It will be P of t is equal to 10, which is the a value, times 2, which is the b value, to the exponent t. Now that we have discovered the equation, we can solve all of the parts of the problem. Part B asks, how many flies are present after 1 week? To solve this part, we first change time in weeks to days. So in 1 week, we know that there are 7 days. Now that we know time equals 7, we can substitute the value into the equation we have just created in Part A, and solve, since the equation relates to the number of flies to time. After doing this, we found that the fly population after 7 days, or 1 week, is approximately 1,280. Next up is Part C. Part C asks, how fast is the fly population increasing after 1 week? Oh, sorry, it seems that I'm getting a message through my earpiece. It looks like we have some breaking news. Just in, when analyzing this question closely, we can see that it's asking what the rate of increase of the fly population is after 1 week. A rate of increase, this means that we must determine the first derivative of our original equation. The derivative is a way to represent rate of change, the amount by which a function is changing at one given point. Therefore, the equation of the first derivative will relate the slope or the rate of change of the function to any point in time, allowing us to solve for how fast the population is increasing after 1 week. To begin this problem, we will first find the derivative. Taking the derivative of an exponential function is fairly easy. All you have to do is take the original function and multiply it by the k value. Unfortunately, we will not be dropping the base today, but instead taking ln of the base, and we do this because this is how the k value is found. In context to this question, the derivative will be p prime of t is equal to 10 times 2 to the exponent t, times the ln of 2, since 2 is the base. You would normally multiply by the whole function by the derivative of the exponent on the base, but since it is equal to 1, will not affect the overall derivative. Now that we have the equation of the derivative, we can solve the question. Now all we need to do is substitute time, 7 days, into the equation of the derivative and solve. After following this process, our team of experts, me, oh God, excuse me, found that after 1 week, the fly population is increasing at a rate of 887 flies per day. The next question they ask is definitely the trickiest, so prepare yourself. It asks, how long will it take for the fly population to reach 500? Don't worry, it seems hard, but I have confidence everyone watching this can do it. To solve this question, we must rearrange for t. With the knowledge that 500 is the population of the flies at this unknown time, this also means we can set 500 equal to p of t, leaving me with 500 equals 10 times 2 to the t. To start rearranging, we will divide out the coefficient so we have one number equated to another. This left me with 50 equals 2 to the exponent t, because I divided the 10 off both sides. Next, we will log both sides. I can feel your surprise. You're probably thinking, no, you can't do that. That's impossible. But in fact, I can. As long as when I make a change, I do it to both sides of the equation, it's okay. Now that I have log 50 equals log 2 to the exponent t, I can use log laws. I can use the log law that log of a to the exponent r is equal to r times log of a. Don't believe me? How else do you explain that log 100 to the exponent 2 is equal to 4, and 2 times log 100 is also equal to 4? That's what I thought. To complete this question, all that I have left to do is divide log 50 by log 2 to isolate for t. Phew! I broke a sweat doing that. It was by far the most difficult question in this episode so far. Although it was difficult, it does not come without success. After following those steps, we found that the time it will take for the population to reach 500 is approximately 5.64 days. Sadly, we are on our last question for this episode. Part E of question 6 asks how fast the fly population is increasing at the time we found in Part D. We have already completed all the hard work needed to solve this question. We now understand that when something asks for how fast something is increasing, it is asking for the rate of change, so we must use the derivative. We also already found the time in the previous question to be 5.64 days. All that is left to do is substitute the time into the derivative equation previously found in Part C and solve. By following these steps and solving, we found that after 5.64 days, the fly population was increasing at a rate of 346 flies per day. Wow! I can't believe we're already done. Overall, we used our knowledge of exponential functions, derivatives, log laws, and how to solve for population or rate of change given an equation at a given time to solve today's problem. Finally, we will discuss what careers may relate to this calculus problem. A problem such as this one directly relates to many problems biological scientists may have to solve in their field of work as it relates to exponential growth. Many biological scientists specialize in specific fields of study. Those who specialize in bacteria or fungus growth would find our solution very useful. They would find themselves doing a solution much like this one when trying to find out how fast a bacteria or fungus culture may be increasing or decreasing, or what their population may be at a given time. This is useful information as it allows them to record characteristics of specific bacteria or funguses, and acknowledge when the growth could be affecting health, in a negative or a positive way. Fun fact, penicillin, a commonly used medication, is used to inhibit bacterial growth. It is actually a fungus, or should I say, fungi itself. I hope you enjoyed today's episode of Calculus Daily as much as I did. See you next time. Katherine Smith, signing off.